Hello everyone, it's Benny, and today we're going to be talking about how to do subtraction. Now, you might think at first we can just jump in and start building all this fancy subtraction hardware, but take a step back, because if you think about it for more than a couple seconds, you'll realize there's a huge issue of jumping in and doing that immediately. And that is, when you subtract two numbers, say 3 minus 5, what do you get? -2. How on earth do you represent -2 in binary? Yeah, exactly. So, before we jump in and start making all these big decisions about how we have to do binary subtraction and yada yada yada, let's take a step back. Let's first solve the problem of how do we represent negative numbers in binary. So, first off, before we do anything else, we're going to talk about negative numbers. Okay, so here I have numbers 0 through 7 listed out in binary. 0, 1, 2, 3, 4, 5, 6, and 7. This is standard binary, which hopefully you know at this point. The issue is, how do we take these numbers and find their negative counterparts? Well, if you worked with real negative numbers before, your first instinct might be, well, in real math, we have negative signs. If we want -2, we have just a negative sign we put in front of it, and it magically becomes -2. You might think, okay, can't we do something similar in binary? Like, say, instead of this last bit right here being, say, this is actually part of the number, say maybe this last bit is a negative sign. So if this bit's on, it's negative. So in that case, our numbers would be 0, 1, 2, and 3, -0, -1, -2, and -3. And, well, there's nothing wrong with that. That's a perfectly valid way of representing binary. There's a couple of weird things to doing negative numbers this way, though. First off, -0. You never, ever end up with a -0 unless you're on drugs. I mean, come on. You don't have -0. So, that's the first weird thing about it. Second thing is, we just spent through all this effort to make our adders work. And we've made really fast adders. Wouldn't it be nice if negative numbers just somehow just worked with our adders as they were? Well, these don't. So if I'd say do 3 plus -3 plus 5. That should give me 2. No, it doesn't. It gives me 16. I'm good at reading binary, don't worry. I believe that's 16, right? Yes, that's 16. Okay. Okay. Yeah, that's not exactly what we want. So this way of representing negative numbers is called sign magnitude notation. There's nothing wrong with it. It's a perfectly fine way of representing binary. But it's probably not the best way. There's probably a better way out there. So, let's try doing it another way. So, another way of doing it is something called 1's complement. The way this works is, well, think about it. -1 is supposed to be the opposite of 1, so why not make it literally the opposite of 1? So, if we want to take 1, find -1, take all the bits and invert them. So, this right here, 1, 1, 0, would be -1. And this -2 right here, if we invert all the bits here, that gets us -2, which is this right here, 1, 0, 1. That's the opposite of this. So it's just taking all the bits. So take any number. I'll take, I don't know, let's take 5. Actually, I don't need an extra bit to actually represent this. Invert all the bits. So, yeah. And this is -5, right here. So this is a really nice way of representing negative numbers, because this inherently works with our existing adders. So, for example, let's say I want to do that -3 plus 5 thing again. So I'll put in 5, and now I need to represent -3. How do I represent -3? Well, 1, 1, 0, 0, right? Because that's the opposite of what I just put in. So if I invert this, you notice this gives me 10001. And that is really, really close to inherently working with our adder. Because if I just ignore that part there, since I'm only doing 4-bit addition, this gets us just one off from what we'd expect. So, what we would actually do if we wanted to do addition with 1's complement is, what we do is we do actually 5 plus 3. We'd invert the 5, and then we would invert the output. And that's actually not working because there's power there, but you notice this gets us 2, just like we'd expect. And there's nothing wrong with this way of doing it either. This is actually a really good way because this way we can take advantage of our really amazing adders that we've already created. And yeah, but the problem with 1's complement is you can still have a negative 0. So if you take 0 and invert it, you get 111. And that's still a little bit weird. So yeah, there's one more way we can do to represent negative numbers. And that's something called 2's complement. And 2's complement is actually a lot like 1's complement. You start off with, say, 1 represent negative 3. So this is positive 3. 1 represent negative 3. I invert it, right? So I'll just put torches to make it simpler. So there's 3. There's negative 3 in 1's complement. To make it negative 3 in 2's complement, all I do is I add 1 to it. And the idea here is that this takes us back. Well, the idea here is if we had negative 0, like 111, if I add 1 to that, that takes us back to just this. So it gets rid of the case of negative 0, and this also inherently works with our adders. So if I wanted to take 3 plus 5 again, so first off I make this negative, so negative 3, I add 1, and that actually takes us back to that, and 3 plus 5 is 2. And I'm ignoring this bit on because I'm only doing 3-bit numbers. But yeah, negative 3 plus 5 is indeed 2. And there you go. So that's how negative numbers can be done in binary. Not that bad, right? Right. So, with all that out of the way, now that we have a way of doing negative numbers, let's look at how we can do binary subtraction. In fact, binary subtraction is really easy at this point, because all we need to do is we need to take our adder right here, and instead of building this new piece of hardware dedicated to subtraction, let's just add the negative version of the second number. Because that's the same thing as subtracting, isn't it? If I want to do 2 minus 3, that's the same as 2 plus negative 3, right? So let's just do that. So what I'm going to do is I'm going to take this, I'm going to add an XOR gate to it. Question is, which XOR gate do I want to do? I'll just do the same one we did before. So actually, I'll do an XNOR gate, just for fun. And, yeah. So, I'm going to build Tommy's XNOR. So I'll start with the NOR part, which is right here. And yeah. So, there's the actual NOR part of Tommy's XNOR. And to get to the X part of it, I do an AND gate. And yeah. And so, to make this into... Well, just to put this in every single bit, I'm going to do like that. That will be the wire that determines if it's negative or not. That'll let me invert it. And I'm just going to take this, and I'm going to stack it with world edit. And you can do this with any adder. So all I'm doing is I'm taking this XNOR gate, and I'm going to invert my input to it. And this will act as a way for me to invert whatever I put in to the adder, which is what I'll put in right here. So this is my input B now. And if I do this, this will let me invert it. And that's the first part of 2's complement. Second part is, well, add 1. Easy way to do this, carry in. Very, very easy way to do that. you notice that adds 1. So now I can easily make an adder and a subtractor in one giant go. So if I want to do the same problem we've been doing the entire time to get rid of these levers because they're no longer relevant, if I want to do, say, 5 minus 3, so first off I'll do 5 and 3. This will just put it into the adder like normal, so I'm getting 5 plus 3, which is 8. Now, what I'm going to do is I'm going to change this to negative 3, which I'll just invert that. There we go, I've inverted it. I'm going to add 1. And you notice this gets us 2, because now it's doing 5 plus negative 3. And it's a very, very nice system. That's the power of 2's complement subtraction. And if you want to, you can do the same process, except invert A and invert output, and you can do it with 1's complement if you prefer. But both ways are perfectly valid ways of doing subtraction. But yeah, that's how you do subtraction. And for fun, I'll subtract something else, just because I have time. So what should I subtract? Let's subtract 56 minus 42, because why not? So there's 1, 2, 4, 8, 16, 32, 64, okay? So 32, 16, 2, that gives me 50. Now to get that's 50 plus 6, that would give me this. So is this 56? 48 plus 8 is indeed 56, okay? 56. Now 42. So I'll go 1, 2, 4, 8, 16, 32, 16, 32, that's 48, that's too much. 32 plus 8, that is, come on, 40, yes, and 2. So now I'm adding them together, and that gets me the wrong answer, probably because I derped up somewhere. But that's okay, or it might be because I'm still subtracting. And it is, so I'm actually already subtracting. Okay, I'm smart. So 56 minus 42 is, well, that is 8 plus 4 plus 2. 8 plus 4 plus 2 is 14. And 42 plus 14 is indeed 56. So this form of subtraction works just like you'd expect. So, thank you. That's how you do binary subtraction. And yeah, hope you enjoyed. I hope you learned. And thank you. See you next time.